Hi, this is Seth, and in this video I'm going to show you how to conduct a t-test in R. I'll show you how to do a one-sample t-test, a paired samples t-test, and an independent samples t-test. Let's start with the one-sample t-test. Over on the left you can see I've already calculated the t-statistic using Excel. Okay, so let's do that in R. I'm going to zoom in a little bit, maybe not that much. Okay, there are many ways to do this, but the fastest way is to start by creating a vector. Oh, and I should just let you know, I don't really code the right way or the way that I don't necessarily code the tidy way or the best practices way. I code in a way that works for me and gets the job done. So if it looks a little different than what you'll see elsewhere, that's why. Now, there are a variety of ways to run a t-test in R. The first thing we might want to do, though, is create a vector, which is like a column or a row of data, kind of like we have this column of data right here. These are our sample scores. This code creates a vector of data, and I'm calling it X. I'm doing this using the C function. That means combine, or some people will say concatenate. It just takes whatever goes inside the parentheses and turns it into a kind of list that's called a vector. This part at the end just says, after you run the code, go ahead and show me what the result is. So when I run that, it assigns that vector of values to X, and here you can see it shows us what they are. That's our column or row of data. Now, the fastest way to do a t-test is to use the t-test function like this, t.test, open parentheses. You can say X, which is the vector of scores that you're running the t-test for, comma. If it's a two-tailed test, you can say alternative equals two-sided, comma. Then enter whatever, well, we should say mu equals, and then you enter whatever value, whatever hypothetical population mean you're comparing your sample mean to. And in this example, you can see I'm comparing it to 50. So I'll just say 50. Then just run that line of code. All right, let's see our results. Yep, looks like R gets the exact same answer that we found in Excel. The t-statistics is equal to 4.09. You can also see it calculates a p-value. This is the probability that we would see an effect at least this large, just due to chance. In other words, if the null hypothesis is true. It also gives you the 95% confidence interval, and you could change that. You could add another argument to your t-test function to specify if you wanted a 90% or a 99% confidence interval. It can do that easily. By the way, if you want to see more about this function, you can use help, open parentheses, t-test, and pull up the documentation, and there you can see all the different ways that you could specify this. I only used some of these arguments. You don't have to use them all. Next, let's look at a paired samples t-test. I don't know, probably also called a dependent samples t-test, maybe, or a t-test for related samples. Here's the scenario on the left. We have two distributions, two samples of scores, and they're connected in some way. Maybe it's the same person at two different points in time. Well, the way this sort of t-test works is we have two columns. We have a t-test formula that works for a single column. So basically what we do is we turn the two columns into one column by subtracting one from the other, and then we just do a t-test like normal. Okay, let's say x1 is equal to, and I'm just going to list all these, 4, 6, 5, 5, 6, 4, 3, 8, 6. Okay. And then x2 is equal to 7, 7, 8, 9, 9, 7, 9, 9, 9. Okie dokie. Okay, we could now run the t-test with a single line of code. So actually, yeah, let's just do that. We can use t-test, except now we're going to enter some different specifications from before. First, enter your first sample of data, that first vector we created, x1, comma. Then your second vector, which we named x2, comma. You could, the way this works, you could just say two-sided right here. That would be a positional argument. If you want, you can spell out the details. You can say alternative equals two-sided. That's fine. But because it's expecting this in the third position, you could just do this briefer code where you just say two-sided, comma, and then we'll say paired equals true. So it's a t-test, but now there are two samples that we're looking at, and we're saying, by the way, they are paired, and it's a two-tailed test. Okay, let's see if it works. The mean difference is -3. That is the same thing we found up here. And our t-statistic is -6, same as we found before. Also, we have a p-value, 0.0003. So not particularly likely if the null hypothesis is true. Okay, cool. Paired samples t-test in R complete. Okay, let's lastly do an independent samples t-test. Now this one is a bit uglier. I switched to calculating these various statistics for the two samples in this vertical fashion because it's just easier for me to grasp that this is the mean of each one, the sample size of each one. Now, if we assume that the variances of the two samples are equal, which I apologize, I'm not going to go into explaining how t-tests work in great depth in this video. This is really about how to do the calculations in R. If we assume the variances are equal, then we might pool them first. We would pool the variances to get a pooled variance right here. And then that's actually what we use to calculate our standard error. But although it's considerably uglier than the others, it's really just the same formula. It's the mean difference. It's the effect divided by the standard error. It's just an ugly standard error. It's an ugly path to get there. So we should be coming to 2.245. Let's see what happens. Okay, first of all, we're going to say, let's create a vector that has these values. Okie dokie. I'll go ahead and run it. Let's do that also for the second sample. Okay. If you want to run it with a single line of code now, as before, you can just say t-test, open parentheses, x1, x2. This is a two-sided t-test, a two-tailed test. And then let's say the variances are equal. So let's say we are assuming that the variances are equal. So we're going through this procedure using this formula. Not necessarily the assumption you want to actually make, but just showing you how to do it. You can say var.equal equals true. So that just means it's going to assume the variances are equal, and it's going to pool them. Okay, I think that's all we need. So let's see what we get. Okay, the mean of x is 9, mean of y is 6, like we expected. Okay, 2.245 is our t-statistic, same as we got right here, except R is rounding for us. Overall degrees of freedom are 14, p-value is 0.041. That looks right. Okay, there you go. Let's do one last thing. Let's say we were not assuming equal variances, which actually is probably safer. We could just say, do a t-test for x1 and x2. It's still two-sided, but we don't have to do anything else. By default, var equal is false. Okay, so I'm just going to leave it out, and it will default. When we do this, everything's the same. It's calculating the same t-statistic, etc., but we use different degrees of freedom, and so the p-value comes out a little bit different, or maybe a lot of it different. But in this case, pretty close. This is called a Welch t-test, when you don't assume the variances are equal. The calculation is actually a lot easier too. You don't have to pool the variances. Okay, cool. More than you wanted to know about calculating t-tests in R. There you go. Have fun.